point in it as this really long branch behind it. Even though that long branch is twice as long as that short branch, they have the same amount of points in them. The short one and that real long one. Why? Because the number of points in a line is infinite. Because a point is infinitesimally small. Now this is the mathematical aspect of it. In reality, no point is infinitesimally small. However, to understand the infinity, we understand the points to be infinitesimally small. And in a line that is 2 inches, there is the same number of points in that line that is 2 inches as a line that is 100 million light years long. That's one of the aspects of infinity that is interesting. In finite terms, I'll use this tree again. Because it also has a top. See all the branches? See all the leaves? See all the foliage on this tree? All the different branches. The bark. The bark is a part of this tree. But it's not the whole tree. The branches are another part of this tree. But it's not the whole tree. The foliage on the tree is part of the tree. But it's not the whole tree. The roots that we can't see that's under the ground is part of the tree. Each of the parts added together equals the whole tree. The branches, the leaves, the foliage, the bark, and the roots. In finiteness, the parts added together equal the whole. In infinity, the parts are the whole. The whole is not greater than the parts with infinity. That's one of the differences between finiteness and infiniteness that we'll get to. Now, I've brought with me about 4 books on the infinite, infinity, mathematics, so on and so forth. George Gamow, 1, 2, 3, Infinity. Very interesting book. On page 17, he says, the infinity of even numbers is exactly as large as the infinity of all the numbers. And the way they show this, I don't know if you can see this or not, hopefully you can. The way they show this is a correspondence. You can see the up and down correspondence between just the finite numbers, the even numbers, as opposed to all the numbers, but there is always a one-to-one correspondence. So even though the even numbers is literally half as much as all the numbers, they are infinitely as great as all the numbers, even though you only have half of them. That's one of the paradoxes of the infinite. And the reason why is because in the world of infinity, a part may be equal to the whole. And that's how George Cantor found that out. You can do a number line. You can put together a number line that has each of the regular numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, all the way off into infinity. And you can do every millionth number. 1 can correspond to 1 million. 2 can correspond to 2 million. You leave 1,000,000 amounts of numbers out, so that it's 1,000,000 times smaller, and yet every millionth number can connect with every natural number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1 million, 2 million, 3 million, 4 million, 5 million, 6 million, 7 million, 8 million, 9 million, 10 million, all the way through into infinity. If it's 1,000,000 times smaller, it is still the same size. They're both infinite. That's fascinating, isn't it? That's George Gamow. Now, another beautiful book on this is Robert and Ellen Kaplan, The Art of the Infinite. And what they say is not only is the theme of a 2-inch line having the same amount of points as a line twice its size, a 4-inch line, namely an infinite amount of points, this can be transferred into all of space. They say all of 3-dimensional space has the same cardinality as the line. That means there are just as many points in the infinite universe as there are on the horizontal bar of this T. See that T right there? The crossbar on it? That tiny crossbar has the same number of points as all of infinite space. Are you feeling your mind being stretched a little? It's heady stuff, this infinity. Now, one of the best groups of books I have ever owned is by James R. Newman, The World of Mathematics. It's a 4-volume set. This one is volume 3. It has an excellent essay by Bertrand Russell on the infinite, and then Hans Hahn on the infinite. Here is what Bertrand Russell says. He says, a collection of terms, this is on page 1558, a collection of terms is infinite when it contains as parts other collections which have just as many terms as it has. You can take away some of the terms of a collection without diminishing the number of terms. Then there are an infinite number of terms in the collection. Infinity plus infinity is infinity. And infinity minus infinity equals infinity. Infinity divided by infinity is infinity. And infinity multiplied by infinity is infinity. That's fascinating, isn't it? It must not suppose that all infinite numbers are equal. Now here's a paradox. They've proven this absolutely. It's in the literature. On the contrary, there are infinitely more infinite numbers than finite numbers. There are different sizes of infinity. The way he puts it is, there are exactly as many points on a line that is a millionth of an inch long as in the whole of infinite space. Whew. Man, that's driving the point home, isn't it? And then one last one. A.W. Moore, The Infinite. Oh, no, I don't have this quote. Oh, yes, I do. Something is infinite if, taking it quantity by quantity, we can always take something outside of it, and yet it remains infinite. These are important concepts to understand with the principles of eternal progression and man becoming like God, because this view of infinity has been challenged by Francis Beckwith. And Richard Hopkins' refutation of Beckwith is absolutely masterful. Oh, I love the smell of junipers. It's wonderful out here among the junipers. I'm up above Cedar Creek, here in the Wolverine Wilderness, enjoying a discussion about infinity, trying to share with you some of the ideas of infinity. This is very interesting because, I'm on the wrong page. If we take a 2-inch line and we stretch it out into a 2 by 2 by 2 by 2, a 4-inch plane, in that 4-inch plane there is an infinite number of those 2-inch lines. That's because a line, by definition, is an infinitely